by special request, a question on turning forces and moments from the AS Physics Mechanics section. Right, first bit of this, which was labelled as question 5 originally, asking you to define the moment of a force, which is force multiplied by perpendicular distance from pivot point. Just to check that you know about that, if you have a force like this, and that's a pivot, then force times distance from the pivot like that. But if the force is at an angle like that, then you have to have the force multiplied by the distance it would have been at had it been perpendicular. So you have to do this. You have to look for a right angle drawn like that, and then the effective distance of that force is only that shorter distance there. So perpendicular distance, they mean how far away the perpendicular that force would be when it becomes perpendicular. So that's it when it's not perpendicular. If you look at this distance there, that's perpendicular distance. So just make sure you know that you do include that word. Now, in this question, we're being given a model bridge on a uniform plank of wood. Essential word uniform means it's the same mass all the way along. So, sorry, it's uniform all the way along, and so the centre of mass, centre of mass will be central. It'll be halfway, all right? And then they've just given us some weights of an object on the bridge, and they've told us that it's supported by these two strings, and that the bridge is not actually supported at all by these two planks. They just sit there. So, by these two supports here, or these two pillars. You don't have to worry about those. There's not going to be any forces involved. Now, first question, they're saying, show and label forces acting on the bridge. Now, I was going to do it on this enlarged diagram, but I think I can do it here. Right, our forces on the bridge are going to be, first of all, easy one to put in, the car itself. Here it is. Right, and I'll call that the weight of the car, and it is 5 newtons, which you can see from your questions. Now, the bridge has got a weight as well, and you know that because the bridge is uniform, you know that its weight acts from its centre of gravity, which is there, and it's 10 newtons, and it's at a distance of 0.5 meters from that end, because that's halfway. And then if you look at the way the diagram is worked, we can figure out that the distance of the bridge, that if that's 0.25, that's 0.5, then this distance here for the distance of the bridge centre of mass is also 0.25 meters. And similarly for the car, that lot there adds up to 0.75. So if that's 0.6, then it works out that for the car, that distance there is 0.15 meters. So we've got all of our distances in there, and so I've labelled weight of the car. I should have said weight of the bridge, maybe write in the words for what those are: weight of the car, weight of the bridge. Then the other things involved are these two strings, and it says label them. Well, I'll put arrows on those two strings. I will call that the tension A. I'll call that tension B. They might expect you to actually write, tension in string A, tension in string B, weight of the bridge, weight of the car. All right. Now, I won't take too much time on it. So to figure out how the part 2, which I just go back to the start again. Right, here we go. By taking moments about point P, what they mean is that's your pivot point, point P. Calculate the tension in string A. So back to here. There's point P. We're looking at forces acting about that pivot. So we're going to have some forces pulling down anti-clockwise, some forces pulling up clockwise. The nifty thing about this is that tension B doesn't come into this because it's acting at the pivot. So tension B, there's no moment due to that at all. Right. Now, my method of doing these moments questions is you think about the principle of moments, right, which will come up in a bit. Principle of moments, not momentum, moments. Principle of moments is that the anti-clockwise sum of them, the SUM, all of them added together, anti-clockwise, will be equal to all of the clockwise moments added together. So anti-clockwise moments added together will be equal to clockwise moments. Now, quick look at this. If that's the pivot, P, then the anti-clockwise moments are going to be the weight of the bridge, right, and I'll put that in as its actual number. Right, I'll put the weight of the bridge in as its actual number there, which is which is 10 newtons. So I've got the weight of the bridge there, which is acting anti-clockwise, 10 newtons multiplied by its distance from P, which is 0.25 meters, and then I will be adding to that, if you like, put that in brackets so you don't get mixed up. I'll be adding to that the moment due to the car, which is the car's weight, 5 newtons, multiplied by the car's weight from P, which I'd mislabeled. That's the 0.15 there, I apologise. That's the 0.15 meters there. So the car's weight is 5 newtons multiplied by 0.15 meters. Again, you can see that if that is 0.6 and that we know is 0.25, right? So if that's 0.25 and that's 0.6, they add together to make 0.85, so the last little bit in there is 0.15. It's just adding up. So this lot is going to equal to the clockwise moments that are acting, which TB doesn't come into it. The only clockwise moment is tension in string A multiplied by its distance from the pivot, which is given 0.5 meters. So work out those, add them together. For the bridge, it comes out as 0.75 Newton meters, and for the car, 5 newtons multiplied by 0.25. Oh, okay, got those the other way around. Okay, sorry, got them the other way around. For the please no, right, sorry, got those the other way around. So sorry, for the bridge, we've got 10 newtons multiplied by 2.5 by 0.25, which comes out as 2.5 newton meters, right? And for the car, it's 5 newtons multiplied by 0.15. That gets you 0.75 newton meters, and if you like, that's going to be equal to 0.5 of TA. So turn the whole thing around, you end up with TA is going to be those two added together, which comes out as 3.25, divide by 0.5, and you get 6.5 newtons. All right, got a random number down there. So that actually gets you the correct answer for tension in string A. That's now 6.5 newtons. We now know it. And the last bit of the question is that once you've got all of these tensions figured out, once you've got that tension figured out, work out what the tension in string B is. So here we go. we know that tension, we know the weight of the bridge, we know the weight of the car, and you don't have to do moments again here. You can just do it by simply looking at the upward and downward forces, because for this bridge to be in equilibrium, the moments have got to sum to zero. The clockwise and the anti-clockwise have got to balance, and the up and down forces, or rather all the forces have to balance. There aren't any horizontal forces, but that means that the upward forces have to balance the downward forces. So I can crudely just write it like this. I can say that the downward forces, which are 10 newtons and 5 newtons from the bridge itself and the car, must be equal to, by the way, this is for part 3, my apologies, that is for part 2. All right, the downward forces, all of that lot must be equal to TA, tension A and tension B. We know what tension A is. It's 6.5 newtons. So we end up with TB is going to be 10 plus 5, 15, minus 6.5 equals 8.5 newtons. So now the whole thing all works out, because those two strings, their tensions added together is the same as the weight of the bridge and the weight of the car. All right, that's quick run through, quickly giving you the way of working out one of these. A lot of them are the same, some a bit more complicated.